Okay, so in our last session, we spoke about arithmetic series, and now we want to talk about this guy, geometric series. Okay, so from from our session that we did weeks ago when we spoke about geometric patterns or geometric sequences, we said that in a geometric sequence, there is a constant ratio. So we mean that a geometric sequence is something that looks like this. So there's 3, and then there's 9, and then there is 27. Okay. We can extend it, and then there will be 81, 81. Okay. So that means that if I convert this into a geometric series, it will be like this. Okay, so this is a geometric sequence, and this is a geometric series. Okay, and if I want to determine the sum of the first four terms, it will be just Sn, which will be 3 plus 9 plus 27 plus 81. Okay, 3 plus 9 is 12, plus 27 is 39, plus 81, I think it's 120. So the answer is 120. Okay, so this is the sum of the first four terms. But then what if you want to determine the sum of the first 1000 terms, or the sum of the first 100 terms? Obviously, that it will not be a good idea for us to sit down and expand the series to get to the first 1000 terms and then add them all together, because it will take us a lot of time. So what we want to do is we want to come up with a pattern, not a pattern, sorry. We want to come up with a formula or a way in which we can simply determine the sum of any numbers without breaking a sweat. So we want to determine Sn such that we can just plug in n for the number of terms, and then we can be able to determine the sum. Okay, so let's consider a general case. In a general case, we know that the first term is a, the second term is a times r, the third term is ar squared. Remember that in a geometric series, you remember that when we spoke about geometric patterns, we said that the difference between term 1 and term 2 is that there is a constant ratio there that we call R. So in other words, we said that T1, T2, I mean, over T1, AR over R, AR over A, actually. Okay. We said that T2 over T1 is equal to R, which is a constant ratio, right? So T2 in this case is AR and T1 is A. So basically this cancels that and we have R. Okay. So that very same principle that was established when we were working with geometric patterns or geometric sequences is what I'm using to come up with this general case for geometric series. Okay, and then we go to the last one. The last one will be AR to the n minus 1. The second last one will be AR to the n minus 2. And then AR to the n minus 3. Okay, so this is equation 1. Okay, so we know that this is number 1, T number 2, t number 3, not t4. Nope, this is not t4. This is t number last, so we call it tn. This is tn minus 1, and then this is tn minus 2. Okay, and this is our equation 1. Now for equation 2, what we will do is to obtain equation 2, we'll take equation 1 and we'll multiply it by r. Okay, so I will have r as n, which will give me ar plus ar squared plus ar cubed. Okay, and then in this particular situation, now I will have ar to the power n, and then I will have ar to the power of n minus 1, and then I will have ar to the power of n minus 2. Okay, so this is equation number 2. Equation 2. Okay, this is equation 2. Okay, now what we want to do now is we want to subtract equation 1 and equation 2. So basically we will say Sn minus Rsn. Okay, with that being said, we'll have a situation like this. We'll have A minus AR, and then we will have AR minus AR squared, and then we will have AR squared minus AR to the power of 3, and then okay, and then we will have AR to the n minus 1 minus AR to the n, and then we will have a r to the n minus 2. I don't think I'll have enough space. Okay, we will have ar to the n minus 2 minus ar to the n minus 1. Okay, that worked out. And then lastly, we will have ar n minus 3 minus ar to the power of n minus 2. Okay, so this is that one. Okay, so basically what we are saying here in this particular situation, we are saying that equation 1 minus equation 2. Okay, equation 1 minus equation 2. That is basically what we did. Okay, so upon doing this, there is something that is very interesting that begins to happen, because we see that this guy and this guy, they're exactly the same and they are opposite signs. So basically they will cancel each other. This guy and that guy, the same happens there. And if we come to this side, this guy and this guy cancel each other as well. This guy and that guy, they do cancel each other as well. So basically this cancels that, that cancels that, this cancels that one cancels that one. Now, very important thing to note is that if I extend the series further in this particular direction, we will find that the following term will cancel this one. And if I do the very same thing here, I extend this series in this direction, the following term, the term before this term, will cancel this one. Okay, so it means that at the end, I will be left with the first term and the last term. So This will simplify to, it will just simplify to Sn minus Rsn is equal to a minus a r to the power of n. Okay, and then we are looking for the value of Sn, so we see that Sn is a common factor, so it'll be 1 minus r, and then we can take out a common factor as well. On this side, there is a being a common factor, so it will be 1 minus r to the power of n. Okay, and then we can get Sn by dividing by 1 minus r on both sides, so a 1 minus r to the power of n, and then we can divide that by 1 minus r. Okay, so this is the equation that we use to determine the sum of any number of terms in a geometric series. But then there's one thing that has to be spoken about, that in this my particular case, I said equation 1 minus equation 2, but then hopefully you can realize that I could have switched them around and I could have said that equation 2 minus equation 1. Okay, so if I switch them around and I said equation 2 minus equation 1, then my equation at the end would look something like this. So it will be r to the power of n minus 1 over r minus 1. Okay, so it is very important to take note of that yes, we said equation 1 minus equation 2, but then we could have easily said equation 2 minus equation 1, and we could have gotten a slightly different result, which is this one. Okay, now these two results, or these two formulas, they are equally important because we use both of them. Now, this guy is used when r, which is the constant ratio, is less than 1. Okay, so if r is less than 1, we use this solution. But then if r is greater than 1, then we have to use this one. Okay, so each time we are faced with a scenario whereby we must determine the sum of any number of terms in a geometric series, one thing that we must decide is whether our constant ratio is greater than 1 or less than 1. And if it's greater than 1, then we have to use the second formula. But then if it's less than 1, we have to use the first one. Okay? So these are the two solutions that we were trying to determine. Okay, so back to our original problem, or our original question, where we had this situation, and then the question was determine the sum of the first 1,000 terms. Okay, now what we know is that from this situation, a is always equal to the first term. So in this situation, a is 3. Okay, so we know that a is equal to 3, and then r is t2 divided by t1. So r will be 3 as well, because 9 divided by 3 is 3. Okay, so now that we have the value of a and the value of r, the other situation or the other decision that we need to make is whether r is greater than 1 or r is less than 1, and r is clearly greater than 1 in this particular situation. So we have to use the second formula, this one. Okay, so we say that S of 100 of 1,000 is equal to a into r to the power of n minus 1 over r minus 1 over r minus 1, and then we know that a is equal to 3, and then we know that r is equal to 3 as well, and then n is equal to 1000 minus 1 divided by 3 minus 1. Okay, so let's see what we get. Let's simplify this a bit further just to make our lives easier. So it'll be 3 3 into 3 to the power of 1000 minus 1, and then it'll be divided by 2, so it'll be 3 over 2, 3 to the power of 1000 minus 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 1. Okay, minus 1, and then we can use our calculators to evaluate this particular situation. Let's see. 3 to the power of 1000. It's giving us errors, so it's producing a number that is so large to a point whereby the calculator cannot be able to display it. But then the